So here are the things I would say that you want to know about trig briefly. You want to know how to, let me pull up my list of things I wrote down here. You want to be able to evaluate angles, or I should say evaluate trig functions of angles. You want to be familiar with the graphs. Desmos is a great tool to use to check on those. So you can graph any trig function in Desmos. Not that we won't graph them. We'll throw up the graphs kind of quickly, but we'll be familiar with the graphs. There's a couple trig identities we want to know. I think I'm going to limit it to that. Yeah, okay. So let's talk about evaluating trig functions first. So there's kind of two special triangles that we keep in mind when we're evaluating trig functions, and they are the following. They are the triangle that comes from half of a square. You take a square that has side lengths. I usually like to pick side lengths 1 and 1. If you cut it in half diagonally, these angles are 45 degrees. And this side length, if you use the Pythagorean theorem, is the square root of 2. All right, 1 squared plus 1 squared equals the square root of 2 squared. That's one of our favorite triangles. So I'm going to draw again on the other side of the board. And then the other favorite triangle we have is the equilateral triangle, although that's not actually the triangle favorite, with side lengths of 2. Right, it's equilateral. That also means the angles, well, I should say, for a triangle, equilateral also means equiangular. All the angles are 60 degrees. It's not always true for other shapes, right? You could have a shape where all the sides of sided shape where all the sides are the same, but not all the angles would be a rhombus. You cut this triangle in half this way. This angle is 30 degrees. This angle is 90 degrees. This side length is 1, and if you use the Pythagorean theorem, 1 squared plus the square root of 3 squared equals 2 squared. So these are our two kind of special triangles we use to find trig functions of various angles. So let me draw them again. So here is the 45, 45, 90 triangle. And again, the sides are 1, 1, square root of 2. And I will point out that 45 degrees is equal to pi over 4 radians. The relationship between, actually, I'm going to take a quick diversion here after I draw the next triangle. The other triangle here is the 30, 60, 90 right triangle, where the side lengths are 1, 2, square root of 3. The way I always remember which way the sides go is the shortest side is always opposite the smallest angle. The biggest side is always opposite the biggest angle, and the medium side is opposite the medium angle. That's always true. For any triangle, the biggest side is always opposite the biggest angle. The smallest side is always opposite the smallest angle. Always true, kind of neat. And just to point out here, 30 degrees is pi over 6 radians. 60 degrees is pi over 3 radians. We often omit writing the rad or the radians because it's assumed. How does this radians things work? Well, the whole idea is that radians are a nice unit of measuring angle because they don't require any sort of unit. Whereas degrees, there's this kind of thing, this degree thing here. What's actually happening is, if you look at a circle, if you have a circle with some radius, let's say you have an angle here. That angle might be some measure of degrees, but you can also say, well, look, let's say, if this is a 60-degree angle, let's just say it's a 60-degree angle. This 60-degree angle is 1/6 of the circle. The circumference of the circle is 2 pi radians. So this length here, we usually call an arc length S. That arc length, well, since this angle is 1/6 of the circle, this arc length is 1/6 of the circumference. So that S value there is 1/6 of 2 pi r. If we reduce that fraction a little bit, it's equal to 1/3 pi, which I usually would write as pi over 3. This blue pen doesn't erase very well. I was forget about that. Pi over 3 radius lengths. So the idea is that instead of saying that this angle is 60 degrees, we can say that the angle is pi over 3 radians, because it's pi over 3 times the length of the radius. That's how long the arc length is. So that's the idea behind radians, is that no matter how big or small your circle is, if you're looking at a specific angle, the arc length for that angle will always be the same amount of the radius. That's why the name radians is used. So these are these special angles, and we can find sine and cosine and tangent and secant and cosecant and cotangent of all of them. I'm not going to do all of them, but I'm just going to kind of point out how they work. So if I want to find sine, and you might remember the very well-known mnemonic device, SOHCAHTOA. So SOHCAHTOA. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. So if I want to find, say, like sine of 60 degrees, that's going to be the opposite over the hypotenuse, which is the square root of 3 over 2. If I want to find the cosine of, say, pi over 4 radians, that's going to be the adjacent over the hypotenuse, which is 1 divided by the square root of 2. We usually rationalize these, so I would multiply by root 2 over root 2 and write it as square root of 2 over 2. If I wanted to find tangent of, say, 30 degrees or pi over 6 radians, that would be, well, tangent is opposite over adjacent, right? So right, for 30 degrees, the opposite side is 1, the adjacent side is root 3. The adjacent side is never the hypotenuse, right? The hypotenuse is always the hypotenuse. The adjacent side is the side next to the angle that isn't the hypotenuse, so it's got to be root 3. So tangent of root pi over 6 is 1 over root 3, which if we rationalize is root 3 over 3. And then to find the other 3 trig functions, cosecant, secant, and cotangent, we have to remember that cosecant of an angle is the reciprocal of sine. Secant of an angle is the reciprocal of cosine. And cotangent of an angle, one way to remember it is the reciprocal of tangent. Other ways to remember it, probably more normal ways, are that tangent of theta can also be thought of as sine of theta divided by cosine of theta, and cotangent of theta is the reciprocal, which is cosine of theta divided by sine of theta. So if I wanted to say, for example, find, I don't know, cotangent of, let's do pi over 3 radians. Well, let's see. Cotangent, really I'm thinking of, here's actually what I'm really doing. I'm thinking the tangent of pi over 3 radians is opposite over adjacent. So cotangent is the reciprocal, adjacent over opposite, which is also going to be root 3 over 3. Or if I wanted to say find, I don't know, secant of pi over 3, well, I'm going to find cosine first. So cosine of pi over 3 is adjacent over hypotenuse, which is 1/2. So it's going to be the reciprocal of 1/2, which is going to be 2. So that's a very, very brief kind of rundown of how to evaluate trig functions of these special angles. You can remember these triangles. That's kind of how I do it. You can also memorize the unit circle, which is maybe less than ideal, but some people are really good at memorizing things. So if that's you, memorize the things. Let me do one thing here real quick. Cool. Come on, pen, don't fall off the table. All right, sorry. And then the other thing I want to do, so let's see. Yeah. So I kind of want to talk about the, let's talk about the graphs of the trig functions just for a second. So if you're looking, so I will also say, I will try to find, let me write myself a note actually here. I will try to find maybe some trig handouts with practice stuff. Find trig practice and post it up on Canvas so that if you guys want more practice, maybe your next quiz they give you guys this weekend will have some extra trig practice for those of you that want to do it, which will not be required. But I mean, the quiz isn't really required. But okay. The graphs of the trig functions are as follows. So when I'm graphing a trig function, I'm actually going to use the unit circle. So here's my unit circle. It's called the unit circle because the radius is 1 and 1 is a unit. So the endpoints are 1, 0, 0, 1, negative 1, 0, 0, negative 1. And if you've, as many of you have seen the unit circle before, the idea here is that if we measure the angle being 0 at the positive x-axis and then pi over 2, 90 degrees, right? So we're going counterclockwise, pi, 3 pi over 2. And if we go all the way around, we get back to a full 2 pi, right? The circumference is 2 pi times the radius. So the angle for a full circle is 2 pi radians. But if your angle is just some theta, this point here is x comma y. At that point there is equal to cosine of the angle theta comma sine of the angle theta. Meaning that in the unit circle, the x coordinate on the circle is always the cosine value of the angle of that particular point you're at. And the y coordinate is always the sine value. So if I wanted to find, say, cosine of pi over 2, I would look at the point, I would look at the x coordinate and say, oh, it's 0. If I wanted to find sine of pi over 2, I would look at the pi over 2, look at the y coordinate and say, oh, it's 1. And if I wanted to find tangent of pi over 2, I would say, I know that tangent is sine divided by cosine. That's going to be 0 divided by 1, which is 0. And if I wanted to find, say, cotangent, I would say cotangent is 1 divided by 0, right? It's cosine divided by sine. I did this wrong. That's wrong. I made a mistake. Tangent is sine divided by cosine, which is 1 divided by 0, which is undefined. Cotangent would be the reciprocal, which is cosine divided by sine, which is 0 divided by 1, which is 0. Sorry about that. But if I was going to try and graph sine, for example, typically graph one full period of a trig function, meaning one full trip around the unit circle for sine, cosine, secant, and cosecant. For tangent, cotangent's a little different. So here's what we're going to do. We're going to look at these 5 important points. So sine of 0 radians is a value of 0. Okay, we're graphing sine. Sine of pi over 2 radians is 1. Sine of pi radians is back to 0. Sine of 3 pi over 2 radians is down to negative 1. And sine of 2 pi radians is back where we started. It should be the same as where we had here. It's back to 0. So here's what the sine function looks like. Or at least here's what one period of it looks like. It's this nice sinusoidal graph. And the cosine function actually looks very similar. Cosine. So yeah, when I'm graphing any trig function, really, I'm going to break it up into 4 kind of equal subsections. Looks like that. Pi over 2, pi, 3 pi over 2, 2 pi, pi over 2, pi, 3 pi over 2, 2 pi. And then sine of 0 is 1. And then, sorry, cosine of, gosh, the word, not coming out right today. Cosine of 0 is 1. Cosine of pi over 2 is 0. Cosine of pi is negative 1. Cosine of 3 pi over 2 is 0. So 1, 0, negative 1, 0. And then cosine of 2 pi is back to 1. These graphs do look very similar. They are very similar. In fact, if you take the sine graph and shift it pi over 2 to the left, it actually is the cosine graph. It's kind of neat. The other 4 trig functions graphs, I know I said we do them, but I feel like they're not as important. So I will I'll show you two of them, and then I'll just mention that the other two look very similar. So the two I'm going to show you are tangent and secant. So if I was going to graph tangent, I would remember that it's sine over cosine. And then I would look at the same four values on my unit circle, the same 4 points. So here's the thing. Tangent of 0 is sine over cosine, so that's 0 over 1, which is 0. Let's say here's pi over 2. Here's negative pi over 2. Here's pi. And tangent of pi over 2 is undefined. It's 1 over 0. So what's happening? Well, as your angles get bigger from 0 to pi over 2, the tangent values get bigger. But here is where I probably should make a little bit of a table. So I got something planned for the next one. So if tangent of, let's see, so I've got my x values and I've got my tangent of x, which is just sine over cosine. So let's look at 0, pi over 6, pi over 4, pi over 3, pi over 2. So tangent of 0 is 0. And remember it's sine over cosine. So now I'm using those triangles that we drew down, but I'm not going to draw them again. So tangent of pi over 6 is sine of pi over 6 over cosine of pi over 6. Sine of pi over 6 is 1/2. Cosine of pi over 6 is root 3 over 2. That's going to be 1 over root 3, which is root 3 over 3, which is about, I don't know, root 3 over 3, it's a little bit bigger than 1/2. Tangent of pi over 4, that's the nice one. Sine of pi over 4 and cosine of pi over 4 are the same. This is going to be 1. Tangent of pi over 3, it's actually going to be the reciprocal of that. Sine of pi over 3 is root 3 over 2. Cosine of pi over 3 is 1/2. That's just root 3. So here's what's happening. The tangent values are getting larger. 0, about 1/2, about exactly 1, about 1.73. And they're getting larger and larger. I know it doesn't seem like they're getting that large, but as you get closer and closer to pi over 2, you're getting closer and closer to 1 divided by 0, which is getting infinitely large. So what's happening as we get closer and closer to pi over 2 is that the tangent values are getting infinitely large like that. And then the same sort of thing is happening as you go to the left to negative pi over 2, except the tangent values are negative. And that's one period of tangent. And then it just looks the same after that. You don't have to know tangent super duper well. I mean, you should know what it looks like this. It's going to come up in the future, but I feel like knowing more than this is probably unnecessary. Okay, let me do one more graph, and then I think we should move on to talking more about derivatives. I am going to come back, though, later on and revisit sine and cosine, which I think one of the teachers definitely talked about for a second, but yeah. So I'm smart sometimes. Planned ahead. Well, not really. I noticed I could do this. So I want to graph secant, and I remind everybody that this is cosine here. So the nice thing is that if I'm graphing secant, secant of x is the reciprocal of cosine of x, meaning I can take my y values and take the reciprocals of them. So watch this. If cosine is equal to 1, or I should say cosine of 0 is equal to 1, then secant of 0 is going to be 1 over cosine of 0, which is 1 over 1, which is 1. And then here's what I'm going to say. As the cosine values get smaller, the secant values are going to get larger, right? If you take 1 divided by a small number, it gets big. So like when cosine, one good example is this, is secant of, what's the number I'm looking for? Pi over 3. Is 1 over cosine of pi over 3. Cosine of pi over 3 is 1/2. It's 1 over 1/2, which is 2. So right about here, where cosine equals 1/2, the secant value is 2. And here's what's going to happen. the cosine values are going to get closer and closer to 0. And when you have 1 divided by a number that's getting super duper 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 small, the whole thing's going to get super duper large. So what we have is a vertical asymptote for secant whenever cosine is equal to 0. And the same is true over here too. So over here at pi, when cosine of pi is equal to -1, secant of pi is going to be 1 divided by -1, which is -1. And so the same sort of things that happen. So basically, as cosine moves closer to the x-axis, secant moves away from the x-axis to a vertical asymptote. And the same kind of thing over here. So that's what secant looks like in red. These kind of, although not actually parabola-looking things, they kind of look like parabolas. They're not parabolas because parabolas don't have vertical asymptotes. But yeah, so that is my very brief, a little bit more than 20 minutes on trig stuff. If you have more questions about trig, please come see me in office hours. I'm happy to talk about trig. I really like trigonometry. I think there's all sorts of cool stuff. I guess I should say 1 or 2 more things. There's a couple identities that you should be aware of. Probably the most important ones are the following. Sine squared x plus cosine squared x equals 1. Here's one of my favorites that the student taught me one time. I know the identity, but they taught me the mnemonic, the way they remember it. 1 plus tangent squared x equals secant squared x. Or in the words of my student, I tan and get sexy. Can never forget that. It's just burned in your mind, unfortunately. So yeah, I tan and get sexy. Perfect. And then probably the last one, maybe not the last one, but the last one I'm going to say for now is sine of 2x is 2 sine x times cosine x. These 3 identities come up pretty frequently, so you should be aware of them. All right, so let's change gears back to all the derivative stuff. And let's see, where do I want to go? There was somewhere specifically I wanted to start. Yeah, let's do one more example with a limit definition of a derivative problem. Although we're definitely going to move from it pretty quickly to talking about the various rules that we've got. So where'd you go? Yeah. So I want to, okay, so there was something here. Oh, sure, yeah, totally. So this is true for secant and cosecant as well as for also for cosecant and sine, right? So just like secant is equal to 1 over cosine, cosecant of x is equal to 1 over sine of x. And I've been asked to repeat what I said about the relationship between secant and cosine. So since they're inverses, as one of them gets large, the other one gets small, and vice versa. So if cosine gets large, the biggest cosine is 1, secant gets small. So the biggest cosine can be is 1, the smallest secant can be is 1 over 1, which is 1. I mean positively. But as cosine gets small, so as cosine gets closer and closer to 0, secant gets larger and larger and larger. Like cosine can be very, very, very close to 0, but not quite. Like cosine can be 0.00001, and secant's going to be 1 divided by that, which is going to be like 10,000. So as cosine gets small, its reciprocal gets large. The same thing is true here. As sine gets small, its reciprocal cosecant gets very large. So the cosecant graph looks very much like the secant graph, just shifted. In fact, it's exactly shifted the same way that cosine and sine are. So sine is the cosine graph shifted pi over 2 to the right. Cosecant is the secant graph shifted pi over 2 to the right as well. Okay. All right. So I had a couple limit definition questions. Yeah, let's phrase it this way. So let's say my function is f of x equal to, I feel like I changed this one from what the person asked. Sorry, 2x squared plus 9. And I want to use limit definition of the derivative to find the derivative. One person asked me a question that kind of had all the steps spelled out. So let's actually do it that way. So theirs was like a 4-part question. It was like, show me all the steps. So the first part was, what's f of x plus h? Okay, well, f of x plus h is 2 times x plus h squared plus 9. We could multiply this out further if you want, right? We could say this is 2 times x squared plus 2xh plus h squared plus 9. And I suppose we could even distribute the 2 and get 2x squared plus 4xh plus 2h squared plus 9. And then the next part of the question was to subtract them. What's f of x plus h minus f of x? So then we do this minus this, and we get 2, right? It's kind of a lot of writing stuff out. Minus this. Now be careful. Writing it that way, I've made a mistake. I need minus all of it. And that's a 9, not a 4. How many of my 9s look like 4s? So then we subtract. We get 2x squared plus 4xh plus 2h squared plus 9 minus 2x squared minus 9. And the 9's cancel. Also the 2x squareds cancel. One thing I want to point out, that someone asked me about a different function that had something like plus 9, and they were a little confused as to what happens to the 9s. Well, they do end up canceling, right? So when you've got like a function like this, where it's something plus 9 or plus a constant, there's nowhere to plug the x in here. So you get the plus 9, but then in the second piece, you also get a minus 9. So the constant term should always cancel out like this when you're doing a limit definition of the derivative. So the second to last part of this question is then to divide by h. So then they say, what's f of x plus h minus f of x divided by h? So we get all of this divided by h. So all of this meaning just this part. So it's 4xh plus 2h squared divided by h. You can either factor out the h and cancel, or you can just divide each term by h. So you got 4xh divided by h is 4x. 2h squared divided by h is 2h. The very last question is, what's f prime of x? So the thing we should do is we should say, oh, well, f prime of x is the limit as h goes to 0 of f of x plus h minus f of x all over h. So that's the limit as h goes to 0. We're not going to write all this work again. We're just going to say, well, there's our f of x plus h minus f of x all over h. So it's the limit as h goes to 0 of 4x plus 2h. H goes to 0, so we get 4x. Normally, the way I would phrase a question like this is use the limit definition to find the derivative of this, and then we would just start off by saying, right, like f prime of x equals the limit as h goes to 0 of this minus, or like I would write, this figure of, f of x plus h minus f of x all over h. And I would kind of do all this work with the limit each step, but doing it this way is also perfectly fine. I will also point out that this answer is definitely in agreement with what we would get if we use the power rule. If using the power rule, the 2 would come down. You get 4 times x to the 1 less power, so you get 4x to the first, and then the derivative of 9, the derivative of a constant, is just 0. I really want to emphasize here, when you have a constant by itself, its derivative is 0. When you have a constant multiplying a function, the constant stays around and multiplies the derivative. So the derivative of 2x squared is 2 times 2x. The derivative of 9 is 0, which gives us 4x plus 0. Okay. Let's see, where else do I want to go? There are lots of questions about how to find equations of tangent lines. You can certainly hit on that. Let's see. Yeah, I think that's the right place to go. So let's talk about finding some equations of tangent lines, which will definitely use the power rule. Ooh, that's a good one. All right, well, we'll do these first two, and then we'll talk about this third one. So here's the first one. I want to find the equation of the line tangent to y equal to 2x minus x cubed at the point. I'm going to change the point. I'm going to change the point to -4 comma. I'm just going to say x equals -4. I'm going to make it harder. So the original question was, so we're trying to find the equation of the tangent line. to this function at this point. The original question was find the equation line tangent to this function at the point, right in blue just to point out, at the point -3, 21. So I want to point out, pun intended, that this version is slightly easier because they've given you the x and y value of the coordinate. My version is slightly harder because they've only given us the x and y. So we need to do a couple of things. When we're trying to find the equation of a line, you need two things. You need a slope and a point. So if you ever see the words find the equation of a line, you should be like, okay, I need the slope, I need the point. How do we find the point? Well, I've already got the x coordinate. I need the y coordinate. That's an excellent question, Marshall. It definitely does say 21, but I can totally see how that could look like a 4. Good point. Hopefully that looks more like a 21. You're welcome, of course. Yeah, always happy to clarify. So to find the point, well, we know that x equals -4. We're going to plug in -4 to find the y value. So y is going to equal 2 times -4 minus -4 cubed, which is going to be -8 minus -64. And -8 plus 64 is 56. So our point is going to be -4, 56. To find the slope, we're going to use the derivative. Right, so the derivative of the function at the point is the slope of the tangent line at the point. So to find the slope, we're not going to use the limit definition unless we're specifically asked to. We're just going to use the power rule. So y prime, our derivative, the derivative of 2x to the first is just 2. The derivative of minus x cubed is going to be minus 3x squared. Right, in each instance, I'm bringing down the power. So I'm getting 2 times 1 times x to the 1 less power is 0. I'm not writing x to the 0 here. The derivative of x cubed is 3 times x to the 1 less power, 3x squared. I should also stress that when your function or when the piece of your function is just a multiple of x, your derivative is just that multiple because 2x is just a straight line where the slope is 2. So the derivative of a straight line where the slope is 2 is just 2. Right, if we're thinking about these kind of separately. So that's your derivative everywhere, but we want to know what the slope is specifically right here. So I'm going to plug in -4 and get 2 minus 3 times -4 squared. Which is not a very nice number, but it's fine. It's 2 minus 3 times 16, which is 2 minus 48, which is -46. And then we have to write the equation of the line. I am partial to using the point slope form. So y minus the y coordinate equal to the slope times x minus the x coordinate. And if I'm told nothing else, I'm going to leave it like that if I can. Most of the time people are going to ask you to solve for y. So if we solve for y, we're going to get y minus 56 equal to distributing the -46, which is not great. I get -46x. And -46 times +4 is going to be, let's see, 46 times 2 is 92. 92 times 2 is 184. Minus 184. And then adding 56 to both sides, we get -46x. Let's see, -184 plus 56 is going to be 134, 128, -128. That's a 46, not a 96. So that's how we would do a question like this. Find the point, find the slope, find the point, find the slope, and then throw them into the equation of the line formula. Let's look at one more. Well, actually, so I want to point out, someone asked me this one, which we may or may not do right this one because I'm curious. Maybe that's why, maybe this is why the person who asked this one asked this one. So there's a similar question where the function given is b is 0.8? No, sorry, that's 128. That is, I can see how that looks. Yeah, I can see from over here how that could look like a negative 0.8 for sure. No, not at all. I know that this is not a perfect world where everything I write, I mean, normally everything I write is hard to read. I'm sure it's extra hard with the video and the whatever. So yeah, it's 46x, negative 46x and minus 128. No need to apologize. So here's the other one, but I don't know if it was clarified to me. So the function given was the square root of 4x plus 7. We want to find the equation of the line tangent to f of x at the point 8, 7. Was it 8, 7? Yeah, 8, 7. And now here's the thing. To do this, we're going to have to find the derivative. To take the derivative of this, we either have to use the limit definition, which I don't want to do unless we have to, or use the chain rule. Does anyone know for this question if there's a specific way you were meant to do it? Does anyone know if you were meant to use the chain rule or maybe meant to use the limit definition? If that's a we don't know, that's fine. I'm going to table this one until we get back to the background to the chain rule. What I will say here is that the process is the same. So regardless, whether or not you're going to find, whichever way you're going to find the derivative. So let's say you found the slope. In fact, yeah, the slope would be, well, I was going to make something up, but that's stupid. I think the slope is 2/7. Not 100% positive, but let's just, okay. The box method. Could you tell me, I don't know what the box method is. I've not heard of that before. Anyway, I'll come back to this one either because I'm not ready to talk about the chain rule yet. Because there's other rules we should talk about first. But let's pretend like we've done the derivative, we got the slope, and then you just say, okay, I got the slope, I've got the point. The equation is going to be y minus 7 equals 2/7 times x minus 8. I'm not 1,000% sure that this is the right slope. I'm pretty sure, but I might have made a small error doing it. That's fine. And then you could do whatever you want with this. So equation of tangent lines just require a slope and a point. Usually the point is either given or you're given the x part, you can find the y part. The slope, you typically have to find the derivative. So find f prime of x. And then after you find it, you plug in your x value. So your slope here would be whatever f prime of 8 is, which I'm pretty sure is this, but you should double check. We'll definitely come back around to this, I think. Definitely maybe. All right, so a couple more examples, and then we'll talk about the product and the quotient rule. Yeah. So let's see, I got that. Yeah. Sure. Okay, let's look at this one. Somebody asked me this question, which I think is worthwhile. I mean, I think all the questions are worthwhile. So no comment on the other ones. I'd be like, oh, they didn't say that one's worthwhile. They're all worthwhile. Let's see. So someone was given this function for the position of, or the height of a ball at time t. So a ball has been thrown from the roof of a building that was 64 feet high with an initial velocity of 80 feet per second. So there's your initial height. The ball is 64 feet high. And there's your initial velocity, which is 80 feet per second. And the questions are as follows. And they give you this equation. They don't expect you to derive this equation yet. The questions are twofold. One, they tell you that the maximum height occurs when the velocity is 0. And we'll talk about that for a second. But they want us to find the maximum height, which is when the velocity is 0. And they also want us to find the velocity when it hits the ground. So here's the thing we need to be aware of. Velocity is speed and direction, meaning we have to kind of think about if the ball is going one way, the velocity is positive. If the ball is going the other way, it's negative. So the ball goes up and then reaches a maximum and then starts going down. So on the way up, like so right here, the velocity of the ball is 80 feet per second. And then as on its path upwards, it's slowing down, right? It's maybe 70 feet per second, and then 60 feet per second, and then 50, and then 40, right? So as the ball goes up and up and up, it's slowing down. And then at the very apex, it stops going up. Its positive velocity is 0. And then it starts going down. Its velocity is, well, I should say its speed is increasing, right? It's slowly falling, and then, right, as it goes, it's going faster and faster and faster. But the thing is here, the velocity is 0, and as we go down, the velocity is getting more and more negative, right? If it's going down, so we've decided together that the upward direction is going to be positive velocity, and the downward direction is going to be negative velocity. So the velocity is negative, 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 very negative. But to go from positive velocity to negative velocity, you have to top out at 0 velocity. So that's why the maximum height is occurring when the velocity is 0. And this actually speaks to a larger phenomenon which we see in calculus, which is that we find a maximum or a minimum of a function by finding where its derivative is 0. Because the derivative of position is velocity. So velocity of an object whose position is described by a function like this is just the derivative of the position function. We're going to use the power rule. The derivative of 64 is 0. The derivative of 80t is just 80. And the derivative of negative 16t squared is negative 32t. And then we want to find where this is equal to 0. So let me just grab this thing here. I want to see what this box method is while I have a chance. Let's see, let me pull it up over here. Oh, I see. So the thing about the box method is it's not that so yeah, it works for certain types of functions. So the box method is fine, but there are going to be other times when we use the chain rule where the box method doesn't really apply. But it's not bad. It's just, yeah, okay, I see what you're saying. So yeah, the box method would work here. Sure, yeah. Yeah, okay, that's fine. Yeah, we'll say stuff about the chain rule, I think, today. Yeah, I see it. Yeah. It's, I would say the box method, another way books write about the box method, it's also called the power rule version of the chain rule. So it's the chain rule, but only for powers of something in a box. All right. So sorry, I was trying to see when is the velocity 0. So we set the velocity equal to 0, and then we're going to solve for t. So 80 equals 32t. T equals 80 divided by 32. 80 and 32 both have factors of 8. So I can reduce to, let's see, 80 divided by 8 is 10, 32 divided by 8 is 4. Oh, they still both have factors of 2. It's 5 halves. So after 2.5 seconds, or 5 halves of a second, we're going to reach our maximum height. Now notice, we haven't answered the question yet. The question was, what is the maximum height? Not when does it happen. We need to define when it happens so that we can figure out what it is. But to figure out what it is, we have to substitute back in this time to the position equation to tell us the height. So we're going to plug in 5 halves and say that S of 5 halves is equal to, well, let's see, 64 plus 80 times 5 halves minus 16 times 5 halves squared is 25 fourths. So let's see, that's going to be 64 plus 80 divided by 2 is 40. 40 times 5 is 200. Minus 16 divided by 4 is 4. 4 times 25 is 100. So we end up with 64 plus 100 is 164 feet high. Okay, that's not too bad. The second question, so basically both of these questions get at what do you set equal to what when you know something is 0? So when you're finding the max height, you're setting velocity equal to 0 to find the time when it happens. When you're finding when the velocity when the ball hits the ground, well, when the ball hits the ground, the height is 0. So we're going to set this equal to 0 to find the time, and then plug the time back into the velocity equation to find the velocity. So if I set this equal to 0, now if the person writing this problem is nice, they've written it in such a way that the stuff is going to factor pretty nicely. And something to be aware of for this, if I write it the usual way, with the highest powers first, a 16, actually a negative 16, will factor out from each of these. 80 divided by negative 16 is negative 5, and 64 divided by negative 16 is negative 4. Ooh, and maybe I'm out of luck. Maybe this doesn't factor. Maybe I wrote something down wrong? No, I don't think so. I thought it was going to factor. Yeah, I can see that now. So definitely this problems like this, oftentimes they're set up in ways to make you think it might factor. Like it'd be really easy to convince yourself that this was a +4 so that you could make it factor, right? I could see really wanting to do that. Don't do that. So bummer. Factoring still is helpful though, because we can either use the quadratic formula for this, or we can just use it for this, or we can divide both sides by negative 16, so that we just have t squared minus 5t minus 4 equals 0. And that's going to be a bit nicer to use the quadratic formula on than these numbers. So let's do that. It's not pretty, but it is what it is. So our time is going to be, let's see, negative 5 plus or minus the square root of negative 5 squared minus 4 times 1. What the heck is going on here? Oh, it's negative 4. Okay, 4 times 1 times negative 4. I see. Okay, over 2 times 1. So we end up with 5 plus or minus the square root of 25 plus 16 all over 2. We do know, so 5 minus the square root of 41 is negative. It wouldn't make sense for it to be hitting the ground backwards in time. So our time is 5 plus the square root of 41 over 2 seconds. And then we would plug that into the velocity equation to figure out what speed it hit the ground at. So and it's not going to be very nice, but if we plug that in there, the velocity at this terrible time is equal to 80 minus 32 times this terrible time, which actually will work out kind of nicely. Here's what I mean. 32 divided by 2 is 16. And then negative 16 times 5 is negative 80. And negative 16 times the square root of 41 is negative 16 root 41. These 80s cancel. So the velocity it hits the ground at is negative 16 times the square root of 40, negative 16 times the square root of 41 feet per second. It should be negative because it's traveling downwards when it hits the ground. If you want, you get a decimal approximation here. 16 times the square root of 41 is about, yes, I know it's 16 times the square root of 41, you stupid calculator. I hate it when this calculator likes to give you like you put in 16 squared root of 41, and it's like, yeah, it's 16 squared root of 41. Okay, how useful. So it's approximately negative 102 feet per second. Okay. Totally, yes. Sorry, so the question I got in privately was, can we just let web work do the algebra? And the answer is generally yes. Sometimes, I personally like to simplify things because it's just kind of how I usually do things. But yeah, I would say if you're worried about simplifying a thing or you just don't want to do it, usually web work you can just enter. Like you could totally have written, right, like 80 minus 32 times 5 plus the square root of 41 over 2 and probably been just fine. I will also say you generally, unless they specifically ask for it, should not give a decimal approximation, right? This would probably not be, even if I went, 102 points, 0.4499. Right? Even over 102.4499, they probably would still say, oh, no, James, you're wrong. It's actually negative 16 squared root of 41, which is not exactly the same number. So only decimal approximations if asked for. Okay. Let's see. Let me look at my list here. Oh, yeah, let's do. There's one last thing I want to look at before we get to talking about the product. Yeah, okay, we're good. Someone asked me this question, which I thought was also definitely worthwhile. If we have y equal to the absolute value of x squared minus 9, and they give us the graph for it. And they also specifically say for x between, what have I got here? Let's say, I'm going to change up the numbers a little bit, -5 to 5. So here's the graph. So here's the thing about absolute values of stranger functions. I know that x squared minus 9 looks like this. And here's good old x squared minus 9. I know they give us the graph, but I just don't want to tell you how to graph it. X squared minus 9 is just your usual x squared function, shifted down 9. So it has a y-intercept at 0, -9, and x-intercepts at plus or minus 30. The way you take an absolute value of anything is anything that's negative gets flipped over to being positive. So what's going to happen is this is going to jump up this way, like that. So if you ever have to graph an absolute value of something, you can just take the original graph, and anything that's below the x-axis, you can flip over to be above the x-axis. So the actual graph looks like this. Oh, except I graphed too much of it because they say the graph is only between x equal to -5 and 5. So 1, 2, 3, 4, 5, 2, 3, 4, 5. So, and I've probably not drawn it to be steep enough. That's fine. Like this. This point looks like it's the same height, but it's really not. I should draw it a little bit higher just to make it look right. Sure. And the same deal over here. Like this. This is the 0.5, 16, and -5, 16. All right, and the question is, where is this function differentiable? Or where is it not differentiable? Well, it's definitely not differentiable at x equal to plus or minus 3. Because at plus or minus 3, what do we have at plus or minus 3? Do we have a cusp or corner? Is there a difference between the two? Yeah, I actually don't know the technical difference between a cusp and a corner. I should look that up sometime. I'm going to say it's not differentiable plus or minus 3 because we have a pointy point. And then I would also say it's not differentiable at the endpoints here because it ends. I feel like that's not as important. Usually this is kind of an artificial situation. Like usually we don't just cut off functions at the end, but it's definitely not differentiable there if it's cut off like that because you don't really have like a tangent line. I don't love that aspect of the question. But I will definitely, I will do a little bit more research when I have a minute and investigate whether this is a cusp or a corner. I feel like, yeah, I don't actually know. Now I'm curious. Anyway, I just want to point out, when you got pointy points, it's not differentiable. This function is continuous on its whole domain though. Right? It's definitely continuous from -5 to 5. There's no breaks, there's no jumps. I can draw the whole thing without lifting my pen off the board. Ta-da, it's continuous. All right, I know I've been teasing all the rules for a while here, so let's talk about the product and the quotient rule. And maybe the chain rule too. So the product rule. I'm just going to tell it to you. So here's the problem with the product rule. Well, not the problem, but here's kind of why we need the product rule. So let's say I want to take the derivative of, here's my derivative notation. I'm going to do something kind of silly. Let's say I want to take the derivative of x to the fourth times x cubed. I know I could multiply these together. Yeah, I think so too, Marshall, but like yes. The problem is with that particular one, it looks kind of curvy, so it looks like it's a cusp, but I think it's still kind of a corner because of the differentiability of things. I'm not sure to answer the question that you're asking me, but yeah, I'll take a look at it and I'll try to have a good explanation for you guys on Thursday. So one way we can differentiate this, the usual way you would do something like this. Someone said, what's the derivative of x to the fourth times x cubed? Well, we would say, well, I know how to multiply those things together. That's the derivative of x to the fourth times x cubed is x to the seventh. And we use the power rule. You get 7x to the sixth. No big deal. So I want to point out that you cannot take the derivative of each part separately and multiply it together. The derivative of x to the fourth is 4x cubed. The derivative of x cubed is 3x squared. And when you multiply these things together, 4 times 3 is 12. And x cubed times x squared is x to the fifth, which is definitely not 7x to the sixth. So I really have to strongly emphasize, I cannot say this loudly enough. If you take the derivative of f times g, it is not equal to the derivative of f times the derivative of g. So what is it then? Well, here is the product rule. The product rule says the following. If you take the derivative of f times g of x, so something you'll write like is f of x times g of x. Take the derivative of f of x times g of x. It's equal to the derivative of the first one times the not derivative of the second one, plus, then you switch it, plus the not derivative of the first one times the derivative of the second one. So whenever you're taking the derivative of a product, it's always one derivative times one not derivative in every way possible, added together. And it works. The derivative of, let's go back to this, the derivative of x to the fourth times x cubed, if we do it this not smart but long way where we use the product rule, it's going to be the derivative of the first part, which is 4x cubed, times the second part, which is 3x, sorry, times x cubed, right? The derivative times the not derivative, plus x to the fourth, times the derivative of x cubed, which is 3x squared. And if we simplify this, 4x cubed times x cubed is 4x to the sixth. X to the fourth times 3x squared is 3x to the sixth. And 4x to the sixth plus 3x to the sixth is 7x to the sixth. And it works. So the product rule works. Yeah. I knew there was a thing I wanted. We need a few more functions to really be able to use it nicely. What I mean by this is, right, there's not a lot of, at this point, we don't really have a lot of functions we know how to differentiate. So, times it, all right. Yeah, let's also talk about the quotient rule. Actually, let me, so product rule, we could do a couple more examples. For example, I could ask, what's the derivative of x to the sixth plus 9x squared times x to the fifth minus 4x cubed? And yeah, normally I would use multiplying it out before I use the product rule, but we could also use the product rule. It's going to be the derivative of this, so 6x to the fifth plus 18x times the not derivative of that, plus, do it the other way, the not derivative of this, x to the sixth plus 9x squared, times the derivative of this, which is 5x to the fourth minus 12x squared. And then you could multiply it out and simplify it. That's not what the point is here, though. I also want to point out that we could use the product rule for something that's really simple. what's the derivative of 6x to the 10th? Well, I'm sure everybody can tell me it is something times x to the something. What's the coefficient going to be? Fine, you guys don't want to play. Yeah, thank you. So yeah, perfect, thanks, yeah. 60 times x to the 9th, or 6 times 10 times x to the 10 minus 1. But what you can actually think about is you're actually using the product rule here, right? If I think of this as, oh, sorry, I wrote, ooh, this is a bad notation here. It's not that the derivative is equal to, it's then taking the derivative of. No, that's, I don't want to taking the derivative of this. Sorry about that. But one way I can think of this is it's really the derivative of 6 times x to the 10th. And so I could use the product rule here and say, okay, well, it's going to be the derivative of 6 times x to the 10th plus 6 times the derivative of x to the 10th. The derivative of a constant is 0. The derivative of x to the 10th is 10x to the 9th. So you get 0 plus 6 times 10x to the 9th, which is 60x to the 9th. So this is why the constant multiple rule actually works. When you have a constant multiple of a function, that's why you get the constant multiple times the derivative of the function. Because the other half of the product rule has you taking the derivative of the constant times the function, but the derivative of the constant just gives you 0. Interesting. What time is it? Okay. Let's also talk about the quotient rule. And I really feel like we need 2 more functions derivatives to be able to really kind of do any meaningful examples. Yeah, sure. So here is the quotient rule. And actually, before I say the quotient rule, let me just say what isn't the quotient rule. So just like you can't take the derivative of a product and just say it's the product of the derivatives, the same thing is true about quotients. If I want to take the derivative of f divided by g, it is not equal to f prime divided by g prime. There is something called L'Hopital's rule that involves limits, where you take the limit of f over g and it's equal to the limit of f prime over g prime. That's not at all the same as the quotient rule. So if you've heard of L'Hopital's rule, it is something that exists where you do the derivative of the top and the derivative of the bottom separately. It's not the same as this. So just try not to confuse them. If you haven't heard of L'Hopital's rule, that's okay. You don't need it yet, but we are going to learn it eventually. So here's the quotient rule. You want to take the derivative of f of x over g of x. It's equal to, here's like people write it, and here's what I say in my head. So people write it as f prime of x times g of x minus f of x times g prime of x all over g of x squared. Some people use like kind of a rhyme, although I wouldn't say it's a rhyme. It's kind of like a signal song. You see low d high minus high d low over low squared. That's not what I would say, but people like to write that low d high bottom derivative of the top minus high d low top thing derivative of the bottom all over the bottom low squared. I actually say out the words I just said. Meaning when I'm thinking about the derivative of f over g, I think of it as the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Those are the words that actually play out in my head every time I do this. So, for example, if I want to find the derivative of, say, I don't know, x cubed plus 5 over x squared minus x, I'm going to have to use the quotient rule. So it's going to be the bottom. I didn't give myself enough room. Let's just write it down here. It's going to be the bottom times the derivative of the top, which is 3x squared, minus the top, which is x cubed plus 5, times the derivative of the bottom, which is x squared minus 1, sorry, not x squared minus 1, 2x minus 1, all divided by x squared minus x quantity squared. And if nobody said to simplify it, I would leave it like this, right? We should only really simplify things if someone tells us to, or if it's like a super obvious implication that like, if your answer ends up being like 2 times 3x to the 5th, you should simplify that to 6x to the 5th, right? But like for this, no, leave it like that unless someone tells you to simplify it. Or you have a reason, like you're trying to solve where it's equal to 0. Sorry, let's see one thing, yeah. So let's look at another example that somebody asked me. I think it's worth a mention here. So what about this function? G of t equal to 8t cubed minus 2t squared plus pi times t minus e cubed, all divided by t squared. I did change it slightly. The problem I was actually asked was an e there. I made the e cubed just for fun. Now here's the thing. Could you use the quotient rule here? For sure. Whenever you have a fraction, you can use the quotient rule. Should you use the quotient rule here? My typical opinion is you should never use the quotient rule if you don't have to. I should rephrase that. You should never use the quotient rule if it's easier not to. Certainly, technically, even for this, if you wanted to, you could rewrite this so you could use the product and the chain rule. My real kind of response should be, if your denominator has one term in it, and you can divide each thing by that term and simplify everything, that's when you should avoid using the quotient rule. So I want to rewrite this. Oops, I'm not taking g prime of t, I'm just rewriting g of t. I want to rewrite this as 8t cubed divided by t squared minus 2t squared divided by t squared plus pi times t divided by t squared minus e cubed divided by t squared. And then I'm going to rewrite this as t cubed divided by t squared is t, so I've got 8t. T squared divided by t squared is 1, so I've got minus 2 times 1. Pi t divided by t squared is going to be pi times t to the first divided by t to the second. We subtract the powers, and 1 minus 2 is t to the negative 1. And e cubed and t squared, we can't subtract those powers because they're not the same base, right? E is just the number that's about 2.7. So this is going to be minus e cubed times t to the negative second. And now we are ready to differentiate all of this using just the power rule. So let's see. Maybe the power rule and the constant multiple rule are okay. So the derivative of 8t is just 8. The derivative of minus 2 is 0. The derivative of pi times t to the negative first, the pi hangs out. And the derivative of t to the negative first is negative t negative t to the negative second. Right, or it's negative 1 times t to the negative second. And then e cubed times t to the negative second, I don't need to use the product rule here. Right? E cubed, although it looks like something, you would say the derivative is like, I don't even want to say it. I don't want to put the wrong thought in your head. We wouldn't use the power rule here. The derivative of e cubed is 0 because it's a constant. But you've got a constant times the function, so then the derivative is just e cubed times the derivative of this, which is negative 2 t to the negative 2 minus 1 is negative 3. And then I would simplify. So this is one where if they didn't say simplify, I would still have to simplify because I cannot not simplify this. We shouldn't write minus 0. That seems silly. We should write this as 8 minus pi times t to the negative second plus 2e cubed t to the negative third. And you can either leave it like that, or you could bring the t's down to the denominator and write it as 8 minus pi over t squared plus 2e cubed over t cubed. That is also a normal way of writing it. I hate this dust that gets under my nails. It's really not pleasant. Yeah, blue pen dust, gross. Okay. So I think we're not going to get to the chain rule today, unfortunately. We'll have to say that for Thursday. Also for Thursday, corners versus cusps. What's the difference, James? Nobody knows. I mean, somebody knows, but I'll have to do a little bit of searching just to kind of find out. Yeah, two functions. They're super important. Actually, yeah, okay, so how do I want to say this? Sometimes people ask us to take a function, a graphical function, and draw its derivative. So I'm going to pick a real easy example. Let's say, I'll even say what the function is. So let's say the function is y equal to x squared minus 1. Yes, we know the derivative is 2x. Here's what x squared minus 1 looks like. Except I probably drawn it a little too. I did not. It's not my best drawing ever. Sorry. Okay. Yeah. Okay. So here's my derivative. My y equals x minus 1. And if I was going to try and draw the derivative without knowing what the function was, here's what I would say. The derivative, when I draw the derivative, the y values are the slopes of the tangent lines. So here, the slope of the tangent line is 0. So on my derivative graph, I have 0. And then over here, the slope of the tangent line is very much positive. Over here, it's very much negative. So it looks like, over here, the slope of my tangent line is maybe like this. Maybe it's a lot or whatever. And over here, it's maybe like this. So it looks like, right, the further right I go, the steeper it gets. So the more and more positive it goes, they go to the right. And the further left I go, the more and more negative it is. So further left, more negative. So it looks like, and it is, a straight line. My line is not looking exactly right. We know it's supposed to be 2x. Mine looks more like x. Oh, well. But the point is, if you think about the slopes of the tangent lines of a graph, you can think about what its derivative looks like. Well, why did I mention this? Well, because there's two important functions I want to see, and I think one of the teachers definitely wrote this in their notes. But let's say I was going to look at the graph of sine of x, which, if you recall, looks like this. So it goes up to 1, then down to 0, then down to -1, then back to 0. So here's your graph of sine. And now let's graph its derivative by using the slopes of the tangent lines. Specifically at the 5 important points here, 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 and here. Well, first of all, point out at this point, at pi over 2 and at 3 pi over 2, the slopes of the tangent lines are 0. So whatever my y prime is, at pi over 2 and 3 pi over 2, the values are going to be 0. And then it looks like at 0, well, it's definitely a positive tangent line. And it does look like the slope is about 1. It is 1. And over here at pi, it does look like the slope of the tangent line is about -1. It is. I should also mention, this tangent line does actually go through the graph. Not super important, but I should say it. And then over here, back at 0, or sorry, back at 2 pi, well, since it's a full period, it should have the same behavior as it does over here. So the slope should be the same. So the slope of the tangent line is also 1. So what's the graph of this derivative? It looks a lot like and is cosine. Right, so the derivative of sine is cosine. Later on, like next class, we might actually show this using the limit definition, but we don't really have time for that right now. So I'm just gonna, yeah, I feel like, yeah, we may or may not. I'm not sure if that's part of the scope of this class or not. So the derivative of sine of x is cosine. And in a similar way, we could show that the derivative of cosine of x is negative sine of x. Right, we could take this graph. In fact, let's just do it real quick. So we take the derivatives of the graphs here. So the derivative of this is 0. The derivative of this point is -1. The derivative of this point is 0. derivative of this point is positive 1. Derivative here is 0. So drawing this one, it looks like the sine graph has been just flipped over, which is the negative sine graph. Okay. So the nice thing now is that now that we have a couple functions that aren't just powers of x, we can actually ask some more interesting derivative questions, like if f of x is x cubed times sine of x, what's the derivative? Oh, we have to use the product rule. F prime of x is the derivative of the first part times the not derivative of the second part plus, and then we flip it, right? We can leave the first part alone and we take the derivative of the second part, which is cosine x. And you should just leave it like this. Some people, not me, like to factor out the x squared or whatever you can. I only factor if I'm trying to like solve this thing equal to 0. This is our derivative. Or what if we were asked to find, I don't know, maybe the derivative of, I was going to say x cubed plus 2x divided by cosine. The thing about this is once you learn how to do the derivative of secant, you should just write this as the derivative of x cubed plus 2x times secant. So let's make it cosine of x plus 6, because then it's much harder to rewrite this. So we're going to use the quotient rule. It's going to be the bottom times the derivative of the top. Some people like to write out the quotient rule in 2 steps. So some people like to write this intermediate step where they say, okay, I'm just going to say it's the bottom times the derivative of the top. So the top derivative, I haven't actually taken the derivative yet, but this is telling me I need to still do that, minus the, so bottom derivative of the top minus top times the derivative of the bottom, all divided by the denominator of the bottom squared. So I would write this as, so then simplifying, right? This stays as cosine of x plus 6. You do need these parentheses, right? Because all of this times whatever is in here. Times the derivative of x cubed plus 2x is 3x squared plus 2 minus x cubed plus 2x times the derivative of this. Derivative of cosine x is negative sine of x. Derivative of 6 is 0. I'm not going to write that. All divided by the denominator squared. And this is how I would leave my answer. You do need this parentheses, but you don't want to simplify this further unless specifically asked to.